Okay, now it's time for our first lesson with the new unit, which is officially called Uniform Circular Motion. And I'll have it up on the screen and define what that is in a bit. But before we get started, I just want to review what you were already reviewing with forces. So hopefully you've already gone through the forces review before you're watching this video. And I just want us to recall what the basic steps to do a force analysis are. All right, so the basic steps, you do a free body diagram. And then a free body diagram is going to tell you something about forces, which then tell you something about acceleration. And so one of the ideas you can get from your free body diagram, if you know something about the forces, it can tell you something about the acceleration. Or if you know something about the acceleration, it might be able to tell you something about the forces. Like, for example, if you know how the forces are unbalanced, you can then use it to tell you, well, I know what the direction of acceleration then is going to be. Or vice versa, say if you knew what the direction of acceleration is, then you know how your FBD is going to be unbalanced, right? So this is a pretty basic idea. It's a pretty fundamental idea with forces. And this is something we were doing all last semester. It's something you used even in just the review that I just had to do right before this, okay? And so I'm going to focus then on acceleration for something that's traveling in a circle. So let's remember what acceleration is in the first place. So remember, velocity is speed and direction, right? It's how fast it's going and what direction it's going, all right? So if you want to say something's velocity, you'd have to say, oh, it's moving 5 meters per second to the north, or moving 10 meters per second to the left, or 3 meters per second in the negative direction. So you say negative 3 meters per second or something like that, all right? And then remember, acceleration means to be changing velocity. Now notice, to change velocity, that could mean changing speed, of course, which is what we've been talking about now for basically the entire school year. But it could also mean changing direction, all right? And this is the aspect we didn't talk as much before about in first semester. And it's this aspect that I want to focus on now. The acceleration that results in changing direction as opposed to a speeding up or slowing down acceleration, all right? And the particular motion that we're going to study that's changing direction is something called uniform circular motion, all right? Uniform circular motion. So uniform circular motion is a type of motion that involves an object traveling in a circle at a constant speed, all right? So just imagine, I'm not sure if you can see my cursor here, but imagine my cursor here is tracing the motion of this object, and it's just moving in a circle at a constant speed. And that's called a uniform circular motion. The uniform word is referring to the not changing speed aspect. And the circular part obviously means it's moving in a circular motion, which means the fact that it's moving in a circle means it's always changing direction, right? Because, for example, you can see right at this moment, it's traveling in that direction, straight up. But a little bit later on, this object's traveling in that direction. So you can clearly see that those two directions are different directions. So when something's moving in a circle, it's clearly changing direction the entire time, all right? So this type of motion is called uniform circular motion. And our job right now, our objective for this particular video is to understand what direction this object, what direction the acceleration is when this object is undergoing uniform circular motion, when this object is changing direction. What direction is the acceleration, right? So let's actually recall what we've already learned from last semester, all right? So for example, when an object is speeding up, you guys should know that the acceleration is in the same direction as the velocity. So for example, if it's moving right and speeding up, you would say the acceleration is to the right. And if it's slowing down, the acceleration is in the opposite direction of velocity. So for example, if it's moving to the right and slowing down, you would say the acceleration is to the left. But the question is, well, what if it's changing direction? What direction is it accelerating? All right. And I'm going to have a couple demonstrations that you're going to think about that will help you figure out what direction the acceleration is when something is undergoing uniform circular motion. All right. And the first demo I used to do in class is I would take a battery operated car. Remember the very first activity, one of the very first activities you did in class was playing with this battery operated cars that would go at a constant speed. But I attach a string to this battery operated car and I tape it down to the center of the table. And then I turn on the car and you will see it actually travels in a circle. Now, I obviously don't have that equipment with me right now, so I can't really show you that. But I did find a video online that replicates the scenario. So I'm about to show that to you right now. Okay, I'm going to show you this video that's going to have a similar setup to what I was trying to show in the classroom. You have a battery operated car and there's a string attached to it. And then you'll see later, this string is attached to a center post. Okay, so I'm going to go ahead and play this video. You can kind of see for yourself what's going to happen, although I'm going to skip ahead. There's a little bit of intro that's going on here. Okay. Okay, that's pretty crazy. I never even knew this activity existed. If you want to see it yourself, if you YouTube tether car, Tether car, you'll see a bunch of videos of this, whatever this thing is called, this activity is called. But all right, I'm going to play this video again, but I'm just going to focus on certain very specific instances. Okay, so once again, you can sort of see this car right here. It's definitely moving in a circle. Now, it's not uniform circular motion because right, obviously at this moment, it's still speeding up. All right, so right here, it's speeding up, but it's definitely moving in a circle. And right here, you see it start to speed up. Okay, but let me back up. Let's pretend like right here, I'm going to pause it right there. So let's pretend right here it was moving at a constant speed. So say he was here, let's pretend here it was going at full speed. So this would be uniform circular motion because it's moving at a constant full speed and is clearly moving in a circle, right? And so now the question is, well, what direction is this object accelerating while it's moving in a circle? And let's just use this one instant right here as an example. So what direction is this car accelerating right at this instant? And to help you answer this question, it may be worthwhile to think about, well, what force is causing it to accelerate? What object is touching it right now that's causing this object to go in a circle, to turn in a circle? And what direction is that force that's causing it to turn in the circle? And if you know the direction of the force that's causing it to turn in the circle, then you'll know the direction of the acceleration, right? So think about what's touching it, what object is touching it, and it should be kind of obvious what object is touching it that's causing it to turn in a circle. And think about what direction the force from the object is on this car, right? And think about the direction of that force and that acceleration during the entire run, in the entire circle, and what that would be, right? So while this is turning in a circle right here, what direction is the force on that car, and therefore what direction is the acceleration on that car, all right? So I want you to think about that. And I'm also going to have show you another activity that will also sort of help you sort of think about what direction the acceleration is when something turns in a circle. All right. Okay, here in my hand, I have a stick. Normally, I would use this to beat my students, but I guess I can't do that now. Okay, what you see here is a tennis ball on the ground now. And if I were to kick it, it should travel, whoops, it should travel at a constant speed in a straight line, right, forever. Assuming there's no friction between the ball and the ground, all right, which there is in real life. But let's just pretend that there is no friction between the ball and the ground, which means it should roll in a straight line forever. And what I'm going to do next is, once I get it moving by kicking it, I'm going to try to hit it with the stick to get it to accelerate. And I'm going to try to give it a series of taps to try to get this ball to go in a circle. Because I'm trying to get this ball to roll in a circular motion as opposed to a straight line. And the idea is that, well, what direction are my taps going to be to cause this object to move in a circle? All right, so I'm going to try that out now. Tap, 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 tap. Okay, so now that you have seen those two examples, it's now time to answer the question with those two scenarios. Well, what direction was the acceleration then in both of those scenarios when these objects were traveling in a uniform circular motion? All right, so let's take a look at the first scenario again, which was where this car was tied to a string. So here's the car, and it's traveling in a circle. And I'd ask you guys to think about, well, what direction is the force on this object that's causing it to turn in a circle? So this should have been pretty clear, like, well, what's causing it to turn in a circle? It is clearly the string that's attached to it, right? And so the question is, well, what direction is that string applying a force onto this car, okay? And I want you to sort of make sure you don't think about what the car is doing to the string, but rather you're thinking about what the string is doing to the car. So what direction is the force of the string on the car at this instant right here? And it should be pretty clear where the string is clearly pulling this car in towards this direction, right? If you could follow my cursor, right? It was pulling from here into there, in towards the center, wherever the string was attached to where that pull was, right? So if you sort of imagine the direction of whatever that string is doing, right, at every moment, you can see that string is pulling this car in towards the center wherever the string is attached to this pole, right? So at every moment in the circle, the string is pulling it in towards the center. So if the force is in towards the center, that should tell us then whether the acceleration while this object was traveling in a circle was in towards the center of this circle, all right? So we're sort of getting some sort of idea that maybe the acceleration, maybe the acceleration is in towards the center of the circle. Let's take a look at the ball example and see if we come to a similar idea. So here's the ball video, right? And if you watch me tapping it, you can imagine where the center of the circle is, probably somewhere down here, all right? And then you can sort of see, am I tapping it towards the center of wherever the circular trajectory of that ball is, all right? And it does seem like that, yes, I am tapping it in towards the center of wherever that big circle is. So if that ball was traveling in this big circle like this, I have to tap it in towards the center of that. It's sort of just like what the string was doing with the car before. The only difference is that this string is pulling it from the inside, whereas I'm tapping it from the outside, okay? But the resulting direction is the same. It's in towards the center of the circle, okay? So I think we've both confirmed with both scenarios, the acceleration is in towards the center of the circle, all right? With the ball example, I want to show you another idea though, okay, about the direction of the acceleration. So let's go back to right here and imagine like what direction is the force, for example, that I did right there? What direction is the force that I had to apply to cause it to turn in a circle, all right? And one of the things you may notice, this ball at that instant was kind of moving in this direction, right? Looks like up and ever so slightly to the left, but in that general direction, right? And notice that I had to hit it in this direction, right? Which is, yes, towards the center, some imaginary center of the circle right here, okay? But I definitely had to hit it that way. And then notice that this object is traveling that direction and I had to hit it that way, all right? Let's sort of see a little bit later, right? So, okay, so right there, this object is traveling in this direction, and notice that I have to hit it in this direction. So this object is traveling this direction, and I have to hit it in that direction. And one of the things I want you to notice with what I'm trying to describe there is that notice that the direction I'm hitting it is always perpendicular to the direction it's traveling. All right. So like, for example, see whatever direction it's traveling, I have to hit it perpendicular to that, perpendicular to that, perpendicular to that, right? And notice the direction I'm hitting it is always perpendicular to the direction it's traveling right at that instant, okay? So the second way we can describe this direction is perpendicular to the direction it is traveling, all right? Now, I want you to sort of think that or understand this not as two separate ideas, but as two different ways of describing the same thing. Like these two things describe the same direction. Like for example, see this series of pictures right here? So look at this instant right here. See the direction it's traveling is the blue arrow. Here's the direction that I'm going to apply a force. And it is perpendicular to that, all right? So notice now it is turned and see this direction is traveling right here. I'm going to apply a force that is perpendicular to that. And see this direction is traveling here. I'm applying a force perpendicular to that. And notice all these red arrows are all pointing towards some sort of center that looks like it's like right about here. All right. So these two things are both describing the same thing. In other words, they're both true and they both describe the same thing. But it's really important that you understand both ideas. All right. That the acceleration is always in towards the center. And if that's going to happen, that has to be perpendicular to the direction it's traveling, all right? I'm going to talk about that second one a little bit more. You can sort of see another reason why that might be true. I'm going to connect it to something we were just talking about before. So here, if this object right here is moving up, so if you apply a force up, which will cause it to accelerate up, all right? Notice that force and acceleration are in the same direction, which means it's going to speed up. If I were to apply a force in the opposite direction, I will cause it to slow down. So notice that applying a force that's neither in the same direction nor in the opposite direction, but just purely perpendicular, causes it to change direction without speeding up or slowing down. So that's why acceleration that's perpendicular causes purely a change in direction without any change in speed. All right. So that's one way you could sort of think about this as why this works. Okay. Now, in order to practice this concept, all right, I'm going to ask you a question now to sort of see if you fully understand this this lesson. All right. So right here we see I have a picture of an object that's traveling in uniform circular motion. All right. Looks like by my arrows, it's a counterclockwise direction. All right. So it's traveling in this direction. And I want us to find the direction of velocity and the direction of acceleration at all four of these locations. All right. So for example, I'll do the first one for you. I'll do this location right here. So I want to know the direction of velocity and the direction of acceleration at this location. So one thing I know, the direction of velocity looks like right at that instant, it is straight up. It is tangential to the circle. All right. And the direction of acceleration is going to be perpendicular to that and towards the center of the circle, which is this direction. All right. So that would be the answer to these two questions for this location. So what I want you to do right now then is to answer the same three questions yourself for these 3 locations here. All right, so why don't you go ahead and pause the video, try to answer A and B for all 3 of these locations. And after you do that, you can unpause the video and I'll show you what the answers are. All right, so go ahead and pause the video now and answer those 2 questions for all 3 of these locations. Okay, well, I'm assuming you've answered these 2 questions for all 3 locations. So the answer for all 3 of them, so this top location, the velocity would be to the left and the acceleration would be down. At this location, the velocity would be down and the acceleration would be to the right. And down here at the bottom, the velocity would be to the right and the acceleration would be up. Okay? So if you were able to answer all 3 of those locations correctly, then I think you should feel pretty good that you understand this objective to know the direction of acceleration when an object is in uniform circular motion. All right, and the answer is always going to be in towards the center, which is perpendicular to the direction of travel. All right, so that does it for this video, and you can go on to the next video if you want.